And I guess I should say I use these omegas, right? But there's also an equivalent representation that I could put here, which would end up being the rotation, the actual rotation matrices themselves. But this notation's a little bit, or using this representation is a little bit easier because of the way it's on the it's either diagonal or it's on the off diagonals. The block diagonal form isn't necessarily unique. It could be similar to another one where they're related by some similarity transform. Okay. So what I write down now is what's called the projection operators. I'm not going to show how they're constructed. I'm going to write down the operators themselves. Now we have a formula that gives us a systematic way of projecting any arbitrary function out into these invariant subspaces. If we knew the block diagonal form, we could use that to write down the projection operators. We don't often have to use this, but in that case, the projection operator would be this. I'll explain it in a second. All right, so in this case, this is a sum over group elements. And then this is the matrix for the ith rep. So let me see, I'll just write this down. My ear rep was this, so it has this block diagonal form. Then these are all matrices themselves. Right? And so that's what I'm talking about here. This is the ith ear rep. So if you already had the, if you had already taken the regular representation, let's say, and written in a block diagonal form or some other way you've gotten it into block diagonal form, then you can compute the projection operator this way so that this would give you back the functions that I just wrote. And I should write this. This is the dimension. You could just use this formula, write it down straightforwardly, and if you did that and you used the block diagonal form we got earlier, you would end up constructing the functions that I just constructed, those 6 functions. This would be a systematic way to generate those. But it all hinges on the fact that you have to already know what the block diagonal form is. And I think sometimes you can get it without going through the process we did. So in that case, you could end up writing down this projection operator. But it turns out in a lot of cases, you don't even need to necessarily project it onto the invariant bases themselves. Right? We just need to project it into that space. And in that case, there's a simpler projection operator. And for that, you only need to know one thing. That one is equivalent to, or that operator so all the things are the same here, except this is the character. We talked about character tables briefly on Thursday, and I'll go through how you construct them, but that's where this comes from. This character is something that you can look up in a character table. So those are things you construct yourself. If you know, you just use characteristics of the group to construct them. It's just a number. But often now you can just look them up, right? And so, for instance, if you were doing something like this, so this is a good book on this kind of thing. It's Group Theory and Quantum Mechanics by Tinkman, but in the back of his book, he has tables for all the groups, all these character tables for the groups, so you can just look these numbers up. I guess the way I think about it is that you have these invariant subspaces, and each invariant subspace is spanned by a set of vectors. So it has, each invariant subspace has its own basis. And this operator would project it into the invariant subspace, but also resolve it in terms of the basis of the invariant subspace. The projection into that invariant subspace, it tells you how to write it in terms of the basis for the invariant subspace. It just projects it in, it just, so you can take this and it's like summing over it and it'll give you this. So in fact, I actually was going to do that in my notes, but you have to use a property, or maybe you don't have to use a property actually. Maybe you can just use the definition of the character table, or the character. But yeah, like he said, if I sum over j, it would actually give me this. So that in some way tells us how to get the character. But anyway, so this would like resolves it to the basis vectors in the invariant subspace. This just projects it out into the invariant subspace, but without separating it out inside the invariant subspace.
Invariant subspace.
Yeah, exactly.